difference time domain method, and it will be delivered by Dr. Debdeep Sarkar, Assistant Professor, ECE Department, IISc Bangalore. I request all the participants to switch off their videos and mute their microphones so that we can manage the event in a better way. Thank you so much. On behalf of IEEE MTTA Student Branch Chapter, Jadavpur University, I'd like to welcome you all to the webinar, to the workshop entitled Different Computational Electromagnetic Techniques and Their Applications. So the session 4 will be starting at 2 o'clock, and the exact title of the session is A Basic Overview of Finite Difference Time Domain Method, and it will be delivered by Dr. Debdeep Sarkar, Assistant Professor, ECE Department, IISc Bangalore. So please be with us. We'll be starting shortly. And in addition, I would also like to request all the participants, please switch off your videos and mute your microphones so that we can manage the event in a better way. Thank you so much. On behalf of IEEE MTTA Student Branch Chapter, Jadavpur University, I would like to welcome you all to the session 4 of the workshop entitled Different Computational Electromagnetic Techniques and Their Applications. So the fourth session will be delivered by Dr. Debdeep Sarkar, who is Assistant Professor in the Department of ECE at IISc Bangalore. And the title of the talk is A Basic Overview of Finite Difference Time Domain Method. We'll be starting within a minute. Thank you so much. Hello, Dr. Debdeep. Can we start?
Yeah, definitely. We can start any time that you suggest. Yeah.
Okay, fine. So, just allow me for 2 minutes. I'll give a brief introduction of you, and then
Yeah.
you can start your talk. Yeah.
Yeah, sure,
So,
sure, sure.
Dr. Debdeep Sarkar completed BE in ETC from Jadavpur University in 2011, and his MTech and PhD in Electrical Engineering from IIT Kanpur in 2013 and 2018, respectively. He has worked as visiting researcher and postdoctoral fellow in Royal Military College of Canada, respectively during March 2017 to August 2017 and November 2018 to February 2020. After that, he has briefly served as assistant professor in the Department of Electrical Engineering, IIT Ropar, from March to July 2020. Dr. Sarkar has currently joined as an assistant professor in the Department of ECE, IISc Bangalore, from August 2020. His current research interests include antenna system design and algorithm development for next generation wireless communication, body area networks, as well as radar systems, wireless power transfer, and energy harvesting applications. Dr. Sarkar has authored or co-authored more than 30 peer-reviewed journals, papers, and more than 50 international or national conference papers so far. He serves as a reviewer in journals such as the IEEE Transaction on Antennas and Propagation, IEEE Transactions on Microwave Theory and Techniques, IEEE Transactions on Vehicular Technology, IEEE Transactions on Communication, IEEE Transactions on Plasma Science, IEEE Antenna and Wireless Propagation Letters, IEEE Letters on Electromagnetic Compatibility, Practice and Applications, IEEE Antenna and Propagation Magazine, and IEEE Access. Dr. Sarkar serves as an associate editor in IEEE Access since December 2019. Dr. Sarkar is the recipient of the URSI Young Scientist Award YSA twice, respectively in the URSI General Assembly GASS 2020 and URSI Asia Pacific Radio Science Conference APIDASC 2019. He has also received Best Paper Awards and travel grants in several conferences and international repute. Dr. Sarkar has been recently selected in the prestigious position of Infosys Young Investigator in the ECE department at IISc Bangalore. So, with this brief introduction, I invite Dr. Sarkar to start his presentation. Before that, I'm just stopping the presentation from my end.
Yeah. That will be yes.
Yeah.
Okay. Yeah. Just give me a moment. I'll start sharing it. Yeah. I hope that my screen is visible to everyone.
Yeah, it's coming. Presentation, Dr. Debdeep Sarkar, but the slides are not visible exactly. Yeah, now it's visible. Yeah.
Now it's visible. Yeah. Oh, yeah. I think I'll keep this small thing below here. Sometimes what happens is the connection gets lost and it's difficult to gauge whether I'm monologuing or not. So can I start, Orthendu?
Yes, you can start.
Yeah, I guess we are on time, so I'll start. So as thanks to Orthendu for the detailed introduction, and well, it's an honor to me and privilege also to give this talk in my alma mater, Jadavpur University, from where I did my bachelor's. So I think I am audible properly. In case there is any issue, I would request Orthendu to just alert me so that I can, So, well, and I think when he requested me and on behalf of my teacher, Professor Bhaskar Gupta, so I thought that it will be a good opportunity for me also to give this particular lecture on the broad title for this two-part lecture is FDTD method overview and application in MIMO system analysis. So my idea was that today, that is in the first lecture, I will be talking about giving the basic overview of this method. Like FDTD, it stands for finite difference time domain. So, and it is as we know from this title of this workshop, like it is one of the computational electromagnetic tools. So I thought that it will be good for young researchers, students, as well as practicing engineers, and even faculty members and everyone to just get some idea about why this FDTD method is actually very much important in this computational electromagnetics community, and how to actually, there are several applications, but it is very important that people understand how it actually functions. So my talk today will be mostly focusing on the overview of this FDTD method, and I hope that at the end of this talk you will get some idea about how you can code it, how you can write your own program that can solve certain computational electromagnetic problems using this finite difference time domain technique. So as I progress, things will become more and more clear. So just before starting my talk, it is good to have a slight PR exercise for my group at IISC Bangalore. So I have recently joined in the ECE department, and we are planning to get this laboratory going for innovation and development in antennas, radars, and electromagnetics. We call it IDEAR. And our aim is to basically, as you can see here, that to resolve problems on antennas, radars, and general electromagnetic problems, like that can be in the classical, that can be in the quantum domain, and which is actually relevant for several things, like starting from the next generation information and communication technology. Then we have healthcare and security and defense applications and energy sector. And the research that we plan, that will have this component and algorithm level as well as system level research. So we are currently actively looking for students and research fellows to join our group. So you can visit, I think the web link is visible, so you can visit our page and see the prospects. And in case you want to get in touch, you can drop me an email and we can take it forward from there. So in IISc, I have taken some of the snaps, so just to show you around a little bit, that this is our iconic main building, and walking around the campus in the serene kind of atmosphere is always nice. This is a view of our ECE building, and I am currently staying in the Centenary Visitors House. So this is a snap from its garden. So before I go into the talk, just I was tempted to some of the glimpses of my previous journey also, and particularly reminisce a little bit about Jadavpur University, where I did my bachelor's in electronics and telecommunication engineering. And this is a photo of us goofing with friends, and this is from our annual convocation. And after that, I spent quite a bit of time in IIT Kanpur. I worked as a master's student and as well as a PhD researcher there under the guidance of Professor Kumar Vaibhav Srivastava. And in my PhD, I worked on this multi-band and wideband MIMO antenna design, and how to implement those antenna systems and characterize them in far field and near field. So as you can see from the title of my talk also, I'll be discussing about the application of this FDTD method for this MIMO system analysis. So I'll talk about that. And then after my stint at IIT Kanpur, I visited in Royal Military College, Canada, where I was privileged to work with Professor Yahya Antar, who is a IEEE Life Fellow and is currently the president-elect. In fact, from the next year, he will assume the role as president in IEEE Antennas and Propagation Society. So this Royal Military College, Canada, you can see it is located at the borderline of the United States and Canada. It's in a small city known as Kingston. And well, at this time of the year, probably you will see the snow and all those things. The temperature is also quite sub-zero at this kind of time. And these are some of the clicks that I took there also. So again, coming back to the hard reality, the research vision in our IDEAR lab, as I mentioned and I have elaborated here, so we are trying to span this broad area. And from this infographic, you can see that it is important to find a synergy between the various topics, like starting from the antennas and to circuits, and also implementation of frequency selective surfaces, which are very important for radome design and all those problems. Then working on some of the relevant issues from Indian perspective, like energy harvesting and wireless power transfer, as well as this wireless body area networks. And from the security perspective, we need to work on the radar systems and the concept of MIMO, that is the multiple input, multiple output technology that spans from the antennas to the radar actually in everywhere where we have this kind of signal processing. So that is kind of our goal. And of course, very important arm of the entire research vision is definitely this computational electromagnetics. And include into that, apart from some of the analytical tools, and we also need to impart our knowledge in artificial intelligence and machine learning. So it requires, as I mentioned, and I'm repeating, that it requires a holistic view, a synergy between the various topics. And definitely in the computational electromagnetics, I think yesterday we had a very nice introduction given by Professor Ratnajit Bhattacharya. So I think we have to understand the fact that the research on computational electromagnetics, in one way, it is on the development of CEM tools, as well as some people like us, we are mostly using these CEM tools for certain kind of problem solving. So both the directions have their importance, individual importance. So we have to understand that, and the research will take its course depending on the requirements. Now, we are currently having these ongoing collaborations with this Department of Avionics, IIST Trivandrum, and Department of Electrical and Computer Engineering in RMC, Canada. And we are planning to have more. And once it's done, then we will have these various collaborations over there. So with this introduction, I hope I did not spend too much time over there. So this is the basic overview of my today's talk. So I will start by discussing about this FFTD as a computational electromagnetic method, and how we can basically introduce it from Maxwell's equations. So here I would like to tell that apart from I think already we have seen some of the lectures on method of moments and a broad overview of the FFTD of all the computational electromagnetic methods. So the interesting part is this FFTD you can actually introduce in an easier way compared to some of the other techniques. Mostly because, and it will be apparent from my today's talk also, that if you have the knowledge of these Maxwell's equations, well, in the undergrad level or the first year of master's courses in most of the institutes, we have some introduction to this Maxwell equation. And if you have little bit of knowledge about this numerical analysis, not much, like you need to understand how the continuous differentiations can be discretized, and you can implement finite difference kind of routines in your any software. You can use MATLAB, you can use some freeware like Scilab also. So if you have those knowledge and little bit idea about the transmission line and the boundary conditions, so you can actually get an essence about this FFTD technique. So I'll try to discuss more and more about it, and that's why I have planned these parts, like how to formulate this one-dimensional FFTD update equations, how to model the source, this concept of PML, that is the perfectly matched layers, and while modeling the different aspects, like how to choose the cell size, how to choose the time step. So I'll try to explain it from the very basics, and then I'll discuss about how to extend that thing into 3D FFTD, and what kind of pertinent issues are there, and what kind of solution strategies different people have tried to implement. And after that, I will briefly discuss about some of the simulation results also. Like here also, I will discuss results, but here I'll tell you how to model a two-dipole system, like a system of two dipoles, which in my opinion can be thought of as a very simple communication block. Like you have one transmit dipole and one receive dipole, and both the dipoles are thin wires. And we know that we can use method of moments and other tools to model that. But I will show you how to do that in FFTD, and in tomorrow's lecture, I will take it up from there. So just to give you, already it has been told by the other speakers, but just to give you a brief overview of this computational electromagnetics tools in general, that we can say that CEM is basically the process of modeling the interaction of electromagnetic fields with physical objects and the environment. And if we look into our day-to-day life and also the various engineering domains, you will find several applications of this computational electromagnetic tools. So it is not something that is purely done out of the purpose of research or knowledge. It has its direct application to design of several systems. So one of such examples, so instead of going too much on language or equations, I'll try to show you some of the cases where we need this computational electromagnetics. For example, you have a large array and you want to model the radiation pattern coming from it, and how to beamform and how to steer the beam to a particular user. So to do this kind of simulation, you need to actually model this kind of large arrays and model the currents in these various antenna elements, and from that you can calculate the radiation pattern. Another thing, like this is mostly you can think from a base station kind of perspective. Then if you look into your own cell phone and you have several antennas sitting over there, so how this radiation is actually affecting the cell phone itself, like this is actually some kind of heat map kind of diagram for the electric field or some other quantity. I do not recall at this moment. But the point is, if you have these antennas excited, and how this current distribution or other field patterns or specific absorption rate kind of things are actually changing, these are a thing. Then in not only antennas, you have several high frequency interconnects, and where you may not be or definitely will not be able to apply simple lumped circuit theory. So you need some tool to actually see the stray radiation from these various interconnects and all those stuff. So how to do that, like from these circuits or from these elements, how to model the interaction of the fields with these physical objects, like from the objects by, I mean, these kind of things. And another part, like this is like shifting our focus from here to the some other domain. Like let's say we have an aircraft and we want to model how the radar cross section of an aircraft is, and this is a very important problem for the defense community. So this radar cross section, and now we have these things are, you can see that in terms of the wavelength, these things are quite small. Like it's probably 1 lambda or 2 lambda, but not much more than that. But in case of a large aircraft, which could be a 55 lambda cross 55 lambda kind of data, so how to model the interaction of the electromagnetic fields with it, and so that we can actually minimize the radar cross section and our enemy cannot detect us. So all kinds of application we need to like I am repeating it again and again, we need to model the interaction of the EM field with these things. So this is another application domain for CEM. Then a very critical thing is this electromagnetic interference. So here also you need to see that whether these transients or ripple and how these radiated emissions can actually affect a nearby circuit. So you see that this is actually happening wirelessly, and you need to go into the electromagnetics domain to do computational electromagnetics domain to actually analyze this kind of situation. And of course, the bioelectromagnetics. So I'm just there, like these are not the only applications, but some applications just to give you an idea that whether we have a cell phone with us and we want to model that how it radiates into our head, and we have to minimize the radiation. So for that, we need to actually get a proper idea of the head phantom model and know about the various dielectric constants and other parameters that are sitting over there. And we need to see how the electric field or the pointing flow is actually working over inside the human head. It can be any other hand model or stuff like that. And this is not only important for our safety and research on the radiation hazards, but also to characterize your cell phone antenna itself. So the companies do this kind of modeling to get an idea about this. So this is also like you can maybe have a look into this article, like what are the differences between various EM simulation numerical methods. And just infographic, it shows that in one axis we have the complexity of the materials, and another axis we have the electrical size. So I think it is already discussed during this workshop that if we go for very large structures in terms of operating wavelength, then we need to go into the tools like physical optics, geometrical optics, and uniform theory of diffractions, and this like method of moments, and integrated some of the hybrid tools also, and this MLFMM kind of tools. So these things are needed when the like kind of asymptotic kind of tools. I'm not repeating all the things that other speakers already mentioned, but when we have let's say we want to the last problem that I showed, that you have a cell phone near your head and you have a very complex dynamics or complex distribution of these dielectric constants and other regions of your cell phone also, like there are some complex circuits. So all that thing, when you want to go into the finite details, these are the full wave techniques like FDTD and FEM. These things are important in that thing. So in my lectures, I will be specifically focusing on this FDTD method. I guess the topics of method of moments and other things are already taken up and will be taken up in the later parts also. So FDTD, as we know, it is finite difference time domain. This is the full form. So I'll be always mentioning it as FDTD. Now, to introduce, like you can ask me that, okay, you are telling us so much about this importance of the tools, but how to get this FDTD formulation and how do we approach a problem? Let's say we want to learn that, okay, how the electromagnetic wave is actually interacting with the medium. So to do that, you need to have a certain like basic premise, like you need to have the idea about how the electromagnetic wave actually acts in a media. So I guess we are familiar with these books, like let's say it be the Jordan Ballman or like D.K. Cheng, and there are books like Sadiku. I have not put the figures for all of them. So we generally learn about the Maxwell's equations, and we are introduced to these mathematical notations where we have our like magnetic field, electric flux density, magnetic flux density, and how these quantities are actually interrelated. We have the space charge density as well as the current density. So we know that these are this Ampere's circuital law, and we introduce this displacement current over here, and this is our Faraday's law of electromagnetic induction, and then we have Gauss's law, and this is the divergence of the B. So my point to, I will not discuss about how these equations came, because that can take a full lecture in itself, or more than one lecture in fact. But I would start that we have these equations with us. Even if you do not have the complete physical interpretation of these things, you can just simply consider that these quantities, let's say this electric field and magnetic field, all these are space-time quantities, and by space-time we see that it is a function of space as well as time. So R is basically the space variable and T is basically the time variable, and this set of equations that I wrote are basically the differential form of the Maxwell equation. And when we do our textbook study, we generally go into the time harmonic case, where we have actually the this assumption that the time variation of these variables are something like e power j omega t. But you should understand at this point that e power j omega t is not exactly a finite time signal. So it is like if you plot it, it is kind of infinitely extended in time. But whenever we operate in any real device, we switch it on at some point and we switch it off at some point, right? And when we switch it on, there is a transient. So although the assumption of e power j omega t gives us very useful results, and that helps us a lot in designing systems, but we should keep in mind that in the real life, we will not always have the time harmonic scenario. So, but only Maxwell equations are not enough to solve any electromagnetic problem. In addition to that, we also need to have the knowledge of the boundary conditions, like how these fields are actually behaving in terms of, like, let's say we have multiple mediums. We have, let's say, air, and we have a dielectric slab, and we want to model how the electromagnetic wave is actually falling into it and getting scattered or getting transmitted, getting reflected. So in order to do that, we need to understand that with these, there are certain boundary conditions that govern the property of the electromagnetic waves inside any medium. So there are these boundary conditions on the tangential components, and I have just written it in a compact mathematical form. But in terms of language, we already know that the tangential component of the electric field is continuous, and the tangential component of the magnetic field is discontinuous by the amount of the surface current. And similarly, we have the boundary conditions on the normal components also. So we know that how to do this kind of thing, and take a pillbox or take this kind of a loop and derive these boundary conditions also. So people who want to brush up these things may are free to go and check out these various books which are generally used. And now we have, let's say we have the Maxwell's equation, we have the boundary conditions, and next we need to have an idea about the constitutive relations. Like here now we are including the medium properties itself, like whether we have the electrical properties or magnetic properties. So how the electric field is related to the electric flux density, and how the magnetic field is related to the magnetic flux density. So these are the parameters like epsilon and mu. Now here I would try to bring your attention to something like this. These equations, I already told that these are space-time quantities, right? But here, if you look closely, so here it is not exactly we cannot say that it is a time domain of or not, because if you look closely, it will be apparently clear that when we have the dispersive medium, so this epsilon and mu will be a function of the frequency. And to get back the time domain relation, then we have to do certain kind of signal processing, and there will be some integration things coming. So we have to be careful about those issues. And another point is, these are very simplistic, but the medium can be anisotropic also. Like depending on the direction of the wave propagation, this epsilon can have various components. So it can be tensor. Like these things are vector, but this can be a tensor, and this can have 9 components. So all the kind of complexities can arise from these constitutive relations. So just to acknowledge the fact that the things get complex, but trust me, I will not go into those complex domains today. I'll be working on that, how to formulate these FDTD equations based on the knowledge of, let's say, this Maxwell's equation, and how to interpret the results, and how to model various things using this constitutive relation, using this knowledge of boundary conditions. So these things will be apparent. Now, early days of FDTD, that again, we need to understand why we needed this thing, and what was the actual motivation behind the people, let's say Professor Ken S.G., who actually formulated the FDTD equations, or let's say gave an idea about how to lead to this kind of framework. So the paper, if you go into your IEEE Explore, and you can download this paper yourself. So this was published in May 1966, and it is heading is Numerical Solution of Initial Boundary Value Problems Involving Maxwell's Equations in Isotropic Media. So you see that already we are in a safe zone. We are working with isotropic media. And initial boundary value problems, these are some important remarks or important portions in the title itself. So the observation, this is very critical, and this we also have to appreciate the fact that the solutions to this time-dependent Maxwell equation in a general form are unknown except for a few special cases. So this is directly lifted from this paper. So this is actually one of the main reasons why we move into the domain of computational electromagnetics, because if we had analytical closed form solution for all the problems, then of course we do not need to go through all this all this trouble of modeling the medium and modeling the equations and all kind of stuff. But because we do not have these closed form analytical solutions except for a few selected problems, we go for these numerical tools. And at that time, he had this observation also, this is from this paper, that because of the limited memory capacity of present-day computers, so by present day, he means at 1966, numerical solution to scattering problem, which is the ratio of the characteristic linear dimension of the obstacle to the wavelength, is still seems to be impractical. Like what he wants to say in simple language, that if your medium is, or if your object under study is very large, or he mentions it as the characteristic linear dimension, if it is very large compared to the wavelength, then the numerical solution will be a problem, because we might not have the computer resources to handle that kind of problem. So, but well, the times have changed from that, and now we are equipped with much better computers thanks to our people in the VLSI, people in the computer science who have incorporated various algorithms. So we have progressed a lot from those stuff. So some kind of problems which at that time people might have thought that okay, it will not be possible or it will be kind of impractical to do using FDTD. We can do that, or we can at least attempt those kind of problems now. But again, that does not mean that you can use FDTD for all kind of problems, for solving all kinds of problems, because each and every method has its own essence and its own usefulness in terms of the application scenario. But these are just some of the observations. So again, I'll go a little bit back and forth that what we are trying to do, we have this Maxwell's equations and knowledge of the boundary condition and constitutive relation, and we want to formulate the FDTD update equation. So let us proceed into that. Now, just to make things simpler, we start with some of the assumptions. Later on, we can bring in those complexities, plug them one by one. But to get the essence of this update equation formulation, it is always important to go for some kind of assumptions. So we go for this assumption that we are basically operating in free space and we are operating in source-free region. So what we do, and we start with the Maxwell's Carl equations only. This is also another important point, that now what we have, let us see what we have here. We remove this J because now we are working in the source-free domain and also lossless kind of free space. So that J part we can ignore for the time being. And also we are, since in free space, so the constitutive relations become very simple in terms of the space-time domain also. So that epsilon naught and mu naught basically are replaced for the permittivity and permeability. Now these equations, you can simply by looking into this, you can see that, and I have just changed the left-hand side to right-hand side kind of thing. So this del D del T term, this is becoming epsilon naught del E del T, and this is curl of H. And this particular term, this is mu naught del H del T minus curl of E. So just simple, it can look into that coupled differential equation kind of thing. The time partial derivative with respect to time for this electric field is related to the curl of the magnetic field. And similarly, the partial derivative of H with respect to time is again related to the curl of the electric field. Now, it is like, since these are vectors, we know, and in Cartesian coordinate, we can decompose them into the three components. So you don't have to do anything because I have already decomposed it, and you can use the curl formula and you can get these three things like del Ex del T, and it is related to this component. Like you can break it down like this, like you can take the X component and you have del Ex del T, and you have 1 by epsilon naught that is coming by dividing this, and then you take this part and this part, subtract this and get the first component. Similarly, you get these three equations. So these are needed when we are dealing with the three-dimensional case. And similarly, you can do it for the magnetic field also. So I will not bother you with the details. But now what we are to start, as I mentioned, that I'll work with the one-dimensional FDTD to start with. So three-dimensional, as you can see, that all these equations that can be too troublesome for a person who is just sitting and looking into some slides. So just to ease you from that burden, I have tried to go for a more simpler case, because the essence of FDTD is actually you can get from the 1D FDTD, and I will take you through that from step by step. So when we talk about this 1D FDTD, what I mean to say is we have a constraint problem now. Like by constraint problem, we mean, and in fact, we encountered this type of situations in our textbook problems also. Like we say that, okay, we have our electric field, only the Z component is there, and we have our magnetic field, only X component is there. So you can see from the axis that this is our H field and this is our E field. So your pointing vector will actually direct towards this. Z cross X will give you this along the Y direction. So when we have this constraint, so you can simply plug in that we have Ex equals to 0, Ey equals to 0, and similarly we have Hy equals to 0 and Hz equals to 0, and you will get these two very nice simple coupled equations. So you have that del Ez del t is minus 1 over epsilon naught del hx del y, and similarly del hx del t is minus 1 over mu naught del Ez del y. So it is the properties of, you can see that the electric field and magnetic field, they are kind of intertwined, like as if they are destined to be like this forever. So this is the most general situation, and now we are not assuming that any time harmonic thing or anything. This is the general space-time situation. So you can use, in terms of the temporal behavior, it can be a pulse-like thing, it can be a Gaussian pulse, it can be a differentiated Gaussian pulse or modulated Gaussian pulse, or a simple sinusoidal signal, anything it can be. And space, now we know we are confining ourselves that our wave is actually propagating along the y-axis. So just to give you some analogy, and physical intuition also, that we start with these two update equations, and I repeat that del Ez del t and del hx del y, and del hx del t del Ez del y. Now we know that in our undergrads or in our master's coursework or PhD coursework, we people who are working in RF engineering domain, we are always dealing with the transmission lines, and transmission lines are very important in design of any systems. And I'll not again digress to the transmission line design or transmission line equations, but just to give you an idea that these equations, this gives a feel, or this is actually since this is a transverse electromagnetic wave kind of propagation, so you can actually see the analogy with the transmission line itself. And if you just brush up, and this is the unit cell for the transmission line, and you have the current and you have the voltage waves in a distributed circuit. So we know that the general telegrapher's equation, we have this variation of this voltage wave along the y as well as along the time. So I am assuming that this is along y direction. It can be along z or x, and nothing, no worries about that. But these equations I have tried to formulate or try to write, I must say, in form of the y propagating wave. And if you rearrange and we assume that lossless, just same as our other situation, we assume that there is no loss or anything. So we make R0 and we make G0, and we can write these simple coupled equations there as well. These are the, so you can have this analogy, or you can have this simple interpretation that our Ez is basically voltage and Hx is basically current. And in the two-wire system, if you just visualize that, okay, the voltage along, if this is y, and you can say this is x and this is along z. So you're actually, it is voltage basically governed by the Ez field, and since it is a two-wire kind of system, you can consider the loop, and your Hx thing will also come up, that how the current is actually related to the x component. So just to have this idea that even if you forget about the Ez or Hx, you simply consider them as V and I, you will get the idea. And you can model, after this lecture, probably if you go back and you can just simply give it a try to write a simple code that will give you an idea about the propagation of electromagnetic waves in a transmission line. So now comes the next part. We have these continuous time equations, but definitely when we want to solve the problems, the computational electromagnetic problems in a computer system, then definitely we need to have an idea, or you need to actually discretize the thing so that it can be stored in terms of the arrays and in the computer memory in terms of some discrete values. So that is why we need to discretize these equations. So the way we go forward is, we know that this is the y and t. These are the two governing variables in our case. So we change the space index to j and the time index to n. And now if you just look into this equation and use simple forward difference kind of rules to discretize both sides. So it should not be too taxing to understand that now you have the Ez differentiated with respect to the time partial. So basically you can see that how I have written it down, that it is basically Ez and at the same location, but the difference is with respect to the time. So this is one step offset. This is n plus half and n minus half. So basically one step offset, and we divide it by delta t. And similarly, here also we have this part constant. This has no problem, but Now we differentiate with respect to space. So here, this superscript, actually by superscript I am denoting time, and this by I am denoting the space. So here you can see the differences in the superscript, and here we have, in terms of the inside this parenthesis, we have the space index, and this is j plus half, and this is j minus half. And in the next thing, again, I'll come about the half business later, but just to complete that discussion, that you can start with this equation. But here, interestingly, you note that these things are basically j plus half and j plus half, because now again derivative with respect to a time, and here I am derivating with respect to the derivating with respect to the time. So n plus 1 and n, so difference of 1 is there. And in this case, this is same, because this is now derivative with respect to the space. So in this case, only this term within the parenthesis is actually getting like a difference by 1. And of course, the division is by this is delta y. So this is the cell size or the grid step in terms of the y direction. So what I do is basically the entire space, I break it down to small regions and small cells, which are each of this delta y size. Just the same we do for the transmission lines also. So this is that delta y. And the time, again, we model it in terms of, instead of a continuous variable, which is basically in terms of this j delta t kind of thing. So it is progressing with the stepping of this delta t. Now you can ask me that, okay, so why this discrimination between this Ez and Hx? Now for Ez, I am saying that I am denoting the time indices by this n plus half and n minus half, all those things. So this half factor is coming with respect to the time, and but in terms of the space, I am saying that it is like j plus 1 or like this for the Ez. But for Hx, I am saying that the time indices by n plus 1, like that half is gone over there, but that half is again reappearing in this thing. So why we do that kind of stuff? So the beauty here, as it will be apparent from the later on also, we actually, when we solve these two equations, the underlying thing that the ingeniousness of E, you can say, or the people who work on FFTD, this being several people, several prolific researchers have worked in this domain. So one of the key idea is that we have to make use of the interleaving of the E and the H field, of the electric and the magnetic field. So what happens is, the location where we are actually trying to find out the electric field in space, that same location, we are not getting the magnetic field. We are magnetic field, we are evaluating at a point that is actually encircled by the electric field. So you can just imagine the situation when we solve, when we go for our, let's say, the Faraday's law, we have the curl of E and we have the del B del T. So what we do is we try to find out the loop in terms of the electric field, and inside that at some point we know that the flux density is changing. It's not that the point exactly where the electric field loop I am considering, I am trying to evaluate the magnetic flux density. So that is the thing, and that is actually reflected in terms of this indices choice, the choice of indices, and gives us an idea about how to program this in your computer. So you just have to have a feeling of that. I will help you in that in the later on, because I have a diagram to explain this interleaving thing. And the same thing with time also. Like in the time, we are not exactly evaluating the electric field at the same instant when the magnetic fields are there. We are using the magnetic field values of the previous time instant to evaluate the thing. And that is a half step, because in the complete FFTD loop, these are the two time instants. Like in the first half, we do this. We evaluate electric field from the magnetic field. In the second half, we do that. So this half business is just to have a physical, you have to interpret it physically like that. So if you, I'll show you the diagram, because I have just spoken in terms of language, which might not be very clear at the first onset, but I'll show a diagram. So before going into the diagram, let us play with these equations a little bit more. So we have these things with us. We want to make it look more simple and more tractable. So we just do the rearrangement. So you can just follow it, maybe just have a look into this slide. So just Ez n plus half of j, and the right hand side will bring this term, and delta t we multiply over here. So this factor, this delta t divided by epsilon naught into delta y, this factor comes out, and this term is nicely sitting. So we have this thing, like we have the Ez field at one time instant evaluated from the information of the Ez field at the previous time instant and the knowledge of the magnetic fields. And similarly here also, like the magnetic field at one time instant, this is evaluated by the magnetic field component at the previous time instant. And again, here this factor is coming like delta t divided by mu naught into delta y, and the information about the electric fields are there. So you can see that the coupling and the interrelated thing is always there, and these are two simple difference equations, nothing more than that. So these equations we now have with us. We have these two things. Now, when people try to write a code using these things, then we have to also store the values in terms of the memory and all. And we know that storing a particular number in terms of a finite number of bits, and we have to encounter several issues. I think people who have little bit of background in the computer science and done some of the course, let's say on C programming, will know that to store an integer and to store a like floating point number, what kind of challenges are there. So to address those challenges, and here actually in the real life, it poses a very interesting challenge. You see that in this case, we have this delta t upon epsilon naught into delta y. And in this case, we have delta t divided by mu naught upon delta y. Now, let us recall the values of these two quantities. This epsilon naught is the free space permittivity and mu naught free space permeability. These are the values. The units are there, but in terms of the values, these are the things. So you can see there is a stark difference in terms of the order of magnitude. And we know that, let's say, in the free space propagating electromagnetic wave, we all read about that, intrinsic impedance and all those things. So we can find out that that is eta naught is actually this 377 ohms. So the main point that I'm trying to make here is the order of magnitude for the electric field components and the magnetic field components are basically not the same. They are different by an amount of these like fractions. So 377, if you divide it, you can guess that how that number will come out to be. So in order to store these two values, there will be challenges like how many. So initially when people worked, they did not have, like, it might not seem to be that much of a big problem with the modern day resources, but at that time people had to think about that. So there was this requirement for normalizing the entire thing. This entire set of equations, these variables came into the picture. So what people thought was that let us normalize the electric field and magnetic field in such a way that the order of magnitude of this Ez and Hx become the same. So very simple solution is to multiply the electric field with this quantity, like root over epsilon upon mu naught, and reformulate these equations so that they can be programmed in the computer. So it's, again, that computational electromagnetics is all about programming these like Maxwell's equations and putting in the proper boundary conditions in a computer system so that you can get the results. It's not going to be solved analytically, it will be solved by a computer. So we need to normalize these field quantities to actually plug those quantities in the computer itself. So we do the normalization. So how to do that? I have derived all the steps so that there is no, like, you don't have to step jump at any point. So this is the starting point. So what we do is, as I mentioned, I want to normalize the electric field. So the steps are like I multiply both sides of the equations by this epsilon upon mu naught. So when we do that, so these Ez things are readily transformed. Like this tilde, this is just the transformed variable. So when I multiply this by this E component, so it becomes this E tilde thing. So Ez tilde, this is there. And now when I do this multiplication, we have a nice thing coming up, like these things are cancelled out and like not cancelled out exactly, like it is transforming into this 1 upon root over mu naught upon epsilon naught, which is actually, you know, that the speed of EM wave in the free space. So now our transformed equation looks like this, like Ez tilde in terms of that in the previous time instant. And here, this thing has been modified into C delta T upon delta Y, and H, we keep it the same. So again, this is, we can simply replace the Hx in terms of the H tilde thing. In the next step, transforming the H equation slightly, like you have to replace these electric fields in terms of the opposite, like Ez. Now I replace it by Ez tilde times mu naught upon epsilon naught. So this factor comes outside. So you can see that these things will be remain same, like Hx here it's becoming H tilde, and Hx here it is becoming again H tilde. But here this delta T upon mu naught upon delta Y, this thing we have to multiply with respect to mu naught upon square root of mu naught upon epsilon naught to get back this thing. So the beauty of this thing is now we are essentially having this Hx equation. Here also the same constant is coming out, this C delta T upon delta Y. So with that, now we are in a position, we are almost there, we are in a position to see how the coupled equations, which were like the continuous time differential equations previously, we have gone through these steps, like we have done the forward differencing, we have readjusted the terms, and now we have done the normalization as well. So now we are in a position to actually plug these things into the computer, just not yet, but in a position. So you can see now we have these two quantities, like Ez at a particular location is being updated by the Ez at the same location but the previous time instant, and some of the H fields that are located nearby it, like the effect, like this Ez is actually in the location J, and this Hx is at J plus half and J minus half. So one step before or one step later on. So that thing, if you, now we are in a position to visualize the space-time grid for the electric and magnetic field components. So as I am repeating the part that it is not that we discretize the grid and we evaluate the electric field and magnetic field at the same location at the same time. No, we actually do a kind of like linked process. We discretize the space with respect to for the electric field and slightly offset locations for the magnetic field. So in this case, and in terms of time also, like in the, this is the time axis, this is the space axis. So these are the like points or demarcations between the regions. So you can see that, okay, this is the Ez grid. So Ez component, this is at the n minus half time step. And these are the locations J, J plus 1, the way we have chosen. I could have chosen the other thing or other way around also, but this is just the convention that I have chosen. So now in the next thing, in the next half step, we have located the Hx field. So the time, point of time and the point of space where the electric fields are evaluated, the magnetic fields are evaluated just half step advanced, like in this case I am saying advanced in terms of time and half step advanced in terms of the space. So let's say we have the J here and J plus 1 here. So using those two information, we now get the value of the magnetic field at the J plus halfth location. And this J minus half is again evaluated by this J minus 1 and J, and that is there. And in terms of and half step, half time step later. So you can visualize it from here also, like I am trying to get it slow from here. So we have this Ez n minus half, that is here, and Hx values like at the J minus half location and J plus half location at time instant half step ahead. So this was n minus half. So this is at n. So this is at n. So with this information, now I can evaluate the Ez at n plus halfth step. So this is this equation, like Ez at n plus half is basically will take the information of Ez n minus half, and like from that it can combine these two things, and you can evaluate the Ez n plus half at this location J. So this is like just a visualization. It might like take some time to fully appreciate the fact, but again I am trying to like be as clear as possible that at the same time, at the same space, we are not evaluating the electric and magnetic fields. They are just staggered. The notation or the term that is basically used is this staggered grid. So slightly offset. There are two independent, like you can treat them as two kind of independent things, like Ez and Hx. They are located separately at separate instants of time, but they are dependent on one another in a sense that evaluation of one quantity depends on that other quantity also. So that is the beauty, or that is the way this one-dimensional FDTD space-time grid is located. So, okay, we have come up to this point, but now for any real medium, we can have this dielectric and all those things as well. So far I was only talking about this E and H. So just a slight, I did not want to take a very general case, but I just chose one thing, like if we have, let's say, a non-magnetic lossless dielectric medium. So I would keep the permittivity as mu naught itself, but the permeability of the medium will be changed by epsilon naught into epsilon r. So lossless, I am not considering the loss components for the time being. So just to show you the complete picture, like we all are familiar with writing the Maxwell equation with the D, E, B and H. So just to give you that feel. So what happens is we know that the equation is del D del T is basically curl of H. So instead of Ez, now we have replaced those quantities by dz. And Ez we evaluate. Once dz is evaluated, we can evaluate Ez from the knowledge of this dz component just by dividing it by this 1 upon epsilon r. But since these are normalized quantities, we also need to define this normalized flux density. So that is done in a way like the flux density normalization is done by this 1 upon mu naught epsilon naught square root of 1 upon this thing. This is how the flux density is actually normalized, so that the normalized flux density and the normalized electric field are also proportional by this simple relative dielectric constant. So you can keep it like, let's say, for free space, it will become 1. But if it is in another medium, you can make it 4, 10, anything like that. And loss, I am not considering. I'm not considering it to be complex at the moment. In terms of H, it is just, since it is non-magnetic, so it is just simply, we normalize it in a way. I think probably I should have mentioned 1 upon mu naught. Probably that term is missed over here. So again, so I have just put a like code snippet, like how these things are actually going to be programmed in terms of this real quantities. So you can write your program in MATLAB and you can get these update equations in a very simple way. Like you first have this vector, like MATLAB, in MATLAB notation I'm talking. So you have these vectors over here. So dz, you can actually maybe if there is some time after the talk, I can just show you the starting portions from the code also. Anyway, so dz we initialize with a 0, and je is the number of points along the z-axis. So while the way we discretize the space. So the number of points by which we discretize the space is same for E and H, just in the terms of physically, we have to appreciate that they are not in the same location. So you cannot perform an operation on the dz and the bx at the same point because they are slightly located offset. But when you store in terms of the computer variable, you don't have to deal with any half or anything. So this is just for our physical understanding. In terms of computer notation, you have to interpret like this. So the step is like, let's say this equation I am taking. So what I am doing is I am actually, I could have chosen the for loop kind of notation, but I have not used that. Why? Because that for loop kind of thing will, if you try to implement it in MATLAB or anything, then it will slow you down. You can use the vectorized notations. So a little bit of vectorized notation, you have to understand that at any location. So I have purposefully chosen this as 2 to JE, and this is also 2 to JE. So at the one point, like it starts from the vector, the numbers are starting from 1, 2, 3, 4. So at the first point, I will come about that what is actually happening. But I have chosen it like this 2 to JE, and this HX, this is also a vector. This is also a vector of dimension, like total JE number of elements. So now we have chosen this differencing, like slightly advanced, since I'm writing it j plus half and j minus half. So here I have written 2 to JE and 1 to JE minus 1. So you can consider that, let's say you have this number of points. I can go back to this diagram. So from here to here, let's say this is 1 and 2, 3, 4, 5 like this. So what I'm doing is from 2, 3, 4, 5, these locations, I am subtracting the values at 1, 2, 3, and 4. This is exactly what is happening over here. So 2 to JE and 1 to JE minus 1. So this differencing, then we are using the previous information about the Ez. So it is basically dz over there. So that information is there, and we are adding it up with the locations where it was there, like from these locations 2 to JE, and here also 2 to JE. So we are doing this kind of operation to get the calculation of D from H. Next, we are calculating the E from the D. So this is just a proportional thing here, which is 1 upon of this epsilon R. And next thing for the B, then again, we are using the similar kind of offsetting, but now the tables have turned slightly. So we are now evaluating the BX 1 to J minus 1. And this is actually 1 to J minus 1 here also from the previous time instant. And then we are using the interleaving like this EZ, we are now taking 2 to JE, and EZ we are taking 1 to JE minus 1. So again, going back here, so here we are actually using these values and subtracting these values from that. So if this is let's say 2, 2, 3, 4, 5, and we have 1, 2, 3, 4. So we are subtracting this 2, 3, 4, 5 location values from the 1, 2, 3, 4 location values. So this is actually, you can like maybe just note it down and you can write your own code and you will appreciate what is actually happening. And to be honest, like this is being generally in any computational electromagnetics course, let's say I got that from in IIT Kanpur, Professor A.R. Harish was our course instructor at that time, and also in IISC Bangalore, Professor K.J. Binoy and Professor Dipanjan Gop, they actually teach this. So this is an exercise that everyone who does a computational course, this has to do. So this is just a 4-5 line code. There are some, of course, the main thing, this is inside a for loop of the total time steps. Like it starts from a for number of time step equal to 1 to the maximum number of time step. But the entire program is a very short one, so you can write it in your own. But now, so far I have just talked about the update equations, but well, you cannot update anything if you do not put in any source thing over there. So what I do is I do a numerical experiment. I make like this y direction. I keep 100 points over here, and I try to discretize the points as 1 millimeter, like the delta y I choose 1 millimeter. And I want to plug in a source at the source location. So this I have taken at the location 30. J equal to 30 I have taken, and I have tried to launch a particular pulse. Like here, it is a simple Gaussian excitation. So its expression is like this, like exponential of t minus t naught upon sigma. Both the quantities are squared. And I choose certain kind of pulse parameters, and I consider this as a very simple free space. And this is, believe it or not, this is the simple code snippet, and that has to run for the total, like starting from the first time to the 1000th time. And we have, like before doing, we need to have some prelude, like we need to initialize these things, these values, these things has to be put on there. But just by simply repeating this thing. And one interesting fact, I will just point out to that also. Like here I have taken this kind of differencing, but in MATLAB there is this function diff. So using that also you can write the code. So it is basically interchangeable. You can write it on your own. So what we do is we launch the source, this kind of source. So how these parameters are actually playing out. So it is not very complicated. So at the 50 delta tth time, it will basically peak. Like if you, the t naught, this value of at the t naught, basically will this pulse will achieve the value of 1, and after that it will fall down, and before that it will start for some time. So this is the time variation of the pulse that is over here. Yeah, so what then do, how much time do I have?
You can continue up to 3:30.
Okay, sure. Yeah, I think by that it will, I want to take some time to explain this part, so I think that will be good for the, yeah. So thanks. So what we do is we put the source over here, and we want to see that how the fields, like so far I was just talking about this update equation and all, but how it is manifested in the real life. If you write the program yourself, you will get, I hope that this animation is also visible. So this is the thing that is happening. Like you can maybe like wait for a moment and see what is happening. So this is the location j equal to 30 where I launched the pulse. So let us again come back. So this is just a small, you can say a movie from 0 to 0.5 nanosecond. So you can see that it starts and then it moves in both directions. Okay. and then certain strange things are happening, like it might be not very directly intuitive what is actually happening. Something is bouncing off the wall and something is there. So now you have to appreciate the fact that so far I am talking about the space and all those things, but I really have not told you anything about how to truncate this space. Like if you go back, what I tell you is the simulation space is 100 delta y. But I do not, like here I have not mentioned what is the condition here. What is the condition at the one left edge of the problem space, and what is the condition at the right edge of the problem space? Nothing is specified. Or is it not? It's like, it might be that something is already specified and that is not apparent from this particular set of code that I have written over here. So I'll come into that. But one key thing that here you can notice that the pulse that I launch over here is only a function of time. So it does not have any directional bias. That means that when we launch the pulse, it can go into the plus y direction, it will go into the minus y direction. It does not know when the computer, I put this information in the computer, it does not know which direction. So numerically what happens is the pulse moves into both directions. So that part is clear. Like from start, it is going into both the direction. And then something is happening, like some like bouncing kind of thing is happening from this wall, and again some bouncing is happening from the source location also. So what are the things that are actually contributing to this kind of phenomena that we have to apply? So there is no computational part is there, computational electromagnetic part is there, but at the same time you have to appreciate the basic physics or the basic electromagnetic boundary condition and knowledge that is actually happening over there. So that I will come step by step. But before going into that, the visualization wise, okay, these movies look interesting and fine, but and it also conveys the message, but like it is a kind of continuously moving. So to get some physical interpretation, we can maybe use some other visualization tools here also, like movies, like getting these plots and getting the snapshot of the field at these various locations and plotting them frame by frame one time after another. That is okay. But what if we wanted to have something like the bounce diagrams? Again, I go back to the basic book that we actually at IIT Kanpur we followed. That is why we I'm repeatedly, but this is given in other books also. So there is no thing to suggest that. This is a tool like this bounce diagram that is actually taken up or adopted by engineers mostly working in transmission lines or on transient analysis of transmission lines. So people who have worked on those kind of problems might be familiar that you launch some pulse at one end, like the generator end, and this is your load end. And now you want to find out that how this pulse is actually going there, bouncing off here and then bouncing up there. So this reflection coefficients actually come over there, gamma L and gamma G, and then it gets squared up. And so this bounce diagram kind of view, since I already told you about the transmission, so we can use the same bounce diagram kind of thing to actually visualize this electric field in our case, which can be a voltage. So I plotted that. What I did, instead of generating a movie, I used all the values of the electric field. I'm only actually, maybe I should have mentioned it here, but you can consider that these are electric field samples, like along the y-axis, these I have chosen. And what I do is after some point of time, at around this, suppose, I think probably around 0.1 nanosecond, maybe you can see it from the movie itself. I'll wait it to start. Yeah, so around 0.1, this kind of splitting of the two pulses in two directions happen. So this is the time axis now, and this is the space axis. So just it is the bounce diagram is generated from the simulation. What I do, I run the simulation for 1000 delta t, and I get the values, and I use MATLAB to simply plot this like diagram. So color scale I have chosen, same as the y-axis over here. So now this red part, it is actually denoting the peak of the pulse, peak of the EZ pulse, peak of the voltage, as per you can understand. And this blue, when it is becoming, so when it is actually positive, like this, then actually we have it as red. And now when it becomes the negative polarity, then I have taken it as blue. So you can notice a very interesting thing, like this thing, pulse is moving in both directions, fine. This is closer to the boundary, so this reaches early. and then it bounces off here. But when it is bouncing off the left wall, it is actually changing the polarity. And then again, when it's coming here, it is also changing the polarity. But in this case, when we have the pulse going to this direction and it is bouncing off this wall, so there is no change in the pulse polarity over there. So that is an interesting thing. But whenever it's coming to this thing, this boundary, then again, when it is getting reflected, it is changing the polarity. Now, what our simple understanding of transmission line tells us, that when we have, let's say, a short circuit, or you can say, like when I'm talking about wave propagation, you can say if we have encountered a PEC boundary condition, perfect electric conductor boundary condition, our reflection coefficient is basically -1. You can do the simple ZL minus Z0 kind of calculation, and you will get the result that why it is -1 at the short circuited boundary, and at the open circuited boundary it is basically +1. So now the beauty of the thing is, now we have unknowingly, it seems that we have created or kind of short circuited boundary condition here, as well as there is a short circuited boundary condition here also. But in this case, we have an open circuited boundary condition. So let's analyze why this is actually happening. The answer lies in the way I wrote the code over here. So you should appreciate that this is just, I wrote this code there is no, what should I say, absolute code or anything. It all depends on how you try to solve the problem and how you later on interpret the results physically or from your experiment. So this code, the way I wrote it, I took the indices like this from 2 to JE, but at the location 1, that is actually the left end. So in our case, basically JE, you can think it up as 100. So I think things will become more clearer to you. So I go from 2 to 100, but at the first location here, I actually keep it, when I initialized it, it is forced to be at 0. And in the entire thing, in no point I am actually updating that thing. But when I am evaluating the magnetic field, I am again using that value. So I am actually enforcing this dz equal to boundary condition through pure computer, like the computer itself, like when you store the values, this condition is actually enforced over here. So dz equals to 0 means basically we are kind of having a short circuit, a short circuit thing over there. Voltage is becoming shorted. And if you notice the way I am updating the magnetic field, the Bx1 at the JE location, like at the JE means at the 100 location, there we are actually enforcing this Bx equal to 0. Actually Hx, you can simply interpret that Hx equal to 0. So basically this is a perfect magnetic conductor, so open circuit. So now the entire bounce diagram will become very clear to you that why this pulse, when it is hitting the left wall, it is actually changing the polarity because of that -1 kind of thing. And when it is hitting here, then it is coming at the same polarity. So this is the interpretation that I got. But what is happening here? Here it was supposed to be our source location. So, but it seems that something is actually happening. Like after some point, when the pulse comes back here, it is actually getting reflected. Again, if you look into the code, you will get your answer. Here, what I am doing is I am putting the dz1, jct. Jct is actually j equals to 30 over here, and I am plugging in the pulse value. It seems very innocuous at that point that, okay, I'm just putting the pulse value over here. What is the problem? The problem is the pulse, this function, the way it is defined, it only takes the one value at the point, like when it is launched, like at this 0.1 nanosecond or like whatever the value of t naught, maybe 50 delta t, whatever I chose. So at that point, basically, we are actually having the pulse as 1 amplitude, but after that, it is going to the 0 value. And it stays like that. So what I am doing is, for whatever time step later, I am enforcing the condition dz equals to 0 over there. So actually, this is called as, like I am trying to introduce very complex, or like, let's say, it might be sound to many experienced people, it might sound a little oversimplified, but I came up with this to just show you that this hard source condition is actually enforced by your function itself. When you plug in this thing over here, you are actually unknowingly enforcing the dz equals to 0. But we can tweak that just by simply doing this kind of manipulation, and this becomes a soft source. So what I do, from the previous value, I add this value. So in this case, it is actually not a hard condition is not enforced, and now you can actually observe that no discontinuity is actually happening over here. So it is the value over here is actually computed from the other values, and it is not enforcing anything on that thing. So that is the thing that I wanted to show here, that the hard source and soft source that will that you can just simple by in terms of the coding, you can use this kind of formulation to get rid of that hard source formulation. But now these boundaries, we have to do something about that, because if we don't do things with that, we will not be, let's say we want to model something, like we want to place a dielectric slab at some location and want to see that what is the transmittance. We want to calculate the transmittance of that slab if we're launching a source at one end. So these reflections that are coming from the edges will actually contaminate our data. So computer cannot do anything. It will run on its own course. The way the boundary conditions are enforced, it will solve you. It will give you some data. But whether that data is actually meaningful for your application, that you have to think. So until and unless we do something about that boundaries over here, then it is not possible for us to get, or for like in most of the situations, we cannot get the meaningful solution. One solution you can think of is, okay, I can keep the boundaries very far and I will not do anything, just keep them very far. But again, you do not have infinite resources. So within these small resources, you have to have some solution to this problem. So that was one of the main hindrances that although the FFTD method was introduced earlier, but until and unless these perfectly matched layer conditions are not discovered or not implemented numerically, people could not use FFTD in a broader scale. So that was one key, you can say, innovation in terms of this thing, the way actually the code was used to solve problems. So I will not go into the detailed formulation because I think I do not have too much time also. So purposefully I kept it like this. So, but I will try to explain it in terms of physics. Like there are this Moore's PML and Berenger's PML. So interested, I will show you the references later on. You can have a look on them yourselves to how these things are done. But from a very physical point of view, let's say from an antenna engineer's point of view, what is actually happening? What we do in our, let's say now I think about the antenna measurement. We do it in an anechoic chamber. Why we do that? To preserve or to prevent the echoes from happening from the walls. Now, to do that, we put absorbers. So I think many of the present researchers and many of my colleagues and my supervisor, they all work in the domain of absorber. So people will know a little bit about how to implement this kind of absorbers for a practical scenario. But now we want to borrow that knowledge into building up these perfectly matched layers in our boundary, which in our case is actually I think this axis is probably wrong. This is space axis. I have mistakenly, when I've lifted from the MATLAB, it has come as time. So please ignore that. So these are actually the space locations. So what is happening over here is we want to put some absorbing layers at these regions. And now how to do the absorbing layers or implement them numerically? That is the challenge. So from that, one of the idea that can readily come into your mind, or people who have little bit idea about the absorber, is that we need to ensure that the wave is actually matched and then it is somehow getting absorbed. So the way it will work is you need to match it with the free space impedance, which in in the observer design community, they use various tools to do that. Sometimes use a material gradient material kind of thing. Or sometimes you can use the meta-surface resonance and stuff like that to achieve that condition. First to match the impinging wave into the system and then make it absorb in the medium. So we do not do any of such thing because we are now working in the computational domain. So what we do is we use some kind of, you can interpret it in this way, that some kind of weighing functions, and you can actually multiply your this dz and multiply your bx in the same way so that they both get attenuated by the same amount. So there is a smooth kind of transition from at these edges. So whenever, so our purpose is to bring down the wave amplitude, very minimal domain, so that even if it some part of it reaches at the edges and gets reflected, it does not come back and corrupt our original simulation data. So that is our objective. And now if we can implement, like these plots I have given, like these 10 cells are given over here. So at this, like starting from the 1 to at the 10, we put some of these perfectly matched layers. And similarly here also, like from the 91 to 100, we put something. So you can see that starting from 1 actually, because MATLAB starts like that. So when we put this PML condition, 10 cell PML, I have just tried to visualize it in this way. So 10 cells here and 10 cells here, you can see that the wave is now going. And here, although here it reached here, but in this case, it fails to reach here because I have put this absorber thing over here. And I have attenuated them by the same extent, the D and B by the same extent. So now I really do not have, very less thing is reaching over here. Something reaches over here and creates a very fine line. So we can kill it off, that we can put some more PML layers over here. We can stack up more absorbers, numerical absorbers, you can say, more numerical absorbers. And now we are like in a pretty good shape. Like you can see the contrast. When there is no PML, you launch the soft source, you get this kind of reflections from the edges, and you can track them by using this bounce diagram tool. But when you have these PMLs implemented, well, you launch it, the pulse goes here and the pulse goes here and it gets absorbed. So just see that what actually happens when I put the PML. Just this movie in this case might help you to do this visualization in a proper way, that no more spurious reflections. So pulse is launched, it travels in this direction, it travels in this direction, and it gets actually attenuated and it reflects back. Very small amount of component is actually reflected back. So this is the way, and you can see that at the locations where it is actually happening. So we have 20, like this 20 is our location. So when after that 20 is reached, it is slowly getting attenuated. So this is a kind of one thing that I wanted to show you over here, that how to implement a very simple code and to see the wave propagation, space-time wave propagation, the purpose of observing that through a simple numerical code. Now, let us, like I talked about some problems. So these problems we generally teach, or they are there when I say we want to measure the reflectance and transmittance from a finite thickness dielectric slab. That kind of problem we generally, in our basic electromagnetics course, we have those kind of problems. So sometimes, like I can quite understand from the mathematical, all those things that can sound a little bit boring. But if you have your own code, so you can now, what you can do is you can plug and play, and you can interpret the results from your physical knowledge. So once you have the code ready, so once I had the code ready, I can just simply put in a lossless dielectric slab with, let's say, epsilon r equals to 10 at this location. And now I want to launch the pulse over here. PMLs are implemented in both the cases so that I get the proper solution. So now you can see very beautiful things. Like, for example, if you have this epsilon equal to 10 over here, it will create, it will change this characteristic impedance or intrinsic impedance of this slab from that of the free space. So now you can calculate from your known formula, eta minus eta naught divided by eta minus eta naught, you can calculate the reflectance. And now you can calculate the transmittance for the first layer, calculate the transmittance from the second layer, and you can get some idea that how much it will be attenuated or how much part is actually transmitted. So, but you can do all the calculations, but parallelly, like for the teaching community, you can also show you, you can also see the visualization. For example, in this case, the pulse propagates here, and actually I do not have the animation ready with me right now, but the pulse propagates here and then it gets reflected and it changes the phase. You calculate the reflectance, you will get the idea of why it is becoming from red to blue, why it is changing the polarity. And now you can see that when it is moving in the dielectric, this is another beautiful observation, that when it is moving in free space, if you go into time, it is propagating a certain direction in a certain speed. From here to reach from here to here, it is taking very small time. So it is actually the phase, like you can see that it is kind of moving fast. in terms of like from the phase velocity kind of thing. Of course, like you can cube velocity will not be, but so it is faster. Like for the same covering the same distance, it is taking less amount of time. But from here to here, if you go inside the dielectric, there is certain slowness, like it has slowed down, so you can interpret the results. So just by writing like how much, like maybe 20 to 30 lines code or 50 lines code, you can simply like model all these things. You do not need to go for any complicated software, anything. So this you can use for your like understanding or for explaining the concept, and also later on for some research purpose also, if you have your own code ready. For the matter of fact, like in like I have interacted with the students here, so in their CM course they like are pretty much write all these codes on their own and run them. So but of course all the life is not that easy, so I'll just take a few moments to like I guess I'm almost 5 to 6 minutes are left, so I'll just wrap it up pretty fast. So how to, like this is very important, that how to determine the cell size and the time step in, let's say, this 1D FDTD kind of scenario. So one important thing that we have to keep in our mind is that when we try to like discretize all these things and we want to get at some meaningful results, so we have to go by some kind of physical constraints, and the theory of sampling and all those things will come in here. Like for choosing the cell size, so initially I just simply choose it as 1 millimeter. I did not bother about anything, but we have to keep in mind that when I have to choose this delta Y, I should have some idea that what is the frequency range that I am going to target, like in terms of the pulse or in terms of, let's say, modulated Gaussian pulse, whatever I want to launch. What is the frequency of the operation, and that will give you what is the minimum wavelength of the system. And there is this rule of thumb that you must have at least 10 points, 10 spatial points per wavelength to actually have the accurate or adequate kind of representation of the electromagnetic phenomena. So these kinds of considerations. So if I choose this cell size first, then I have to think that I have to know beforehand that okay, I cannot go beyond this frequency or something like that. Another important thing is that time step. Of course, after cell size, we need to go into the time step. So EM wave, we cannot, like we are operating in a numerical, like on a computer domain. So, but we have to keep into mind that this EM wave in propagating in free space, in this case, we chose free space, it cannot go faster than the speed of light. So to propagate a distance of one cell, it actually needs a time like cell size divided by c. So this is the time needed if I am talking about the free space situation. So we have to choose this delta t accordingly, and the quantity like this ry, if you recall the previous equation, there was this quantity c delta t upon delta y. This we have to choose. In our case, we chose it less than 1, like 0.5. So in the general, like again, you can go into the books for the general theory. There is this Courant Frederick Lefy CFL criteria, which if Umax is your maximum phase velocity, then the delta t is actually constrained by this particular equation. Like I am talking about in the 3D, like for 1D, we only had this delta y, but for the 3D, we have delta x, delta y, and delta z. So this is the constraining condition over here. A little bit about this thing, just 1 or 2 minutes, because I will not, maybe if there is interest, I can, in the next part, I will start from that a little bit. So for the 3D also, if we like, we have to interpret all these spatial grids, but you can quite understand that if I had started from the 3D, so it would have been very much complicated, and to visualize that how all the components, you can see now we, in the 3D case, we have EX, EY, EZ, and HX, HY, HZ, all those things, but straight away, it might not be very intuitive, but if you go into this thing slowly, then you will probably have a feel of how the grids are chosen. And of course, there are several issues, like we have to implement medium with loss. We have to include, let's say we want to have a like planar circuit, so we want to include the circuit component. So there are ways to do that, how to implement in a let's say a filter, we want to implement a varactor diode, or you want to implement a chip kind of a resonator. So how to model all these kind of things in FDTD, they are a dedicated theory. And then once we get the time domain waveforms, how to post process all those things to get the space like S parameters, or calculate the currents and recalculate the patterns, how to do the Fourier transform, all those things will slowly it will. If you want to get a broad overview of the FDTD method, of course you need to have several lectures. And of course there is this, I think this point was also mentioned yesterday by Professor Ratnojit, I guess, about the parallelization and this use of FPGA and the GPU. So a little bit, well, my exposure to FDTD, during my undergrad, I was fortunate, like at that time, the project and all those kind of stuff. I wanted to, like, I got this topic actually. At that time, I did not have much idea. So Professor D.R. Poddar, and I was like monitored by Professor Rudra Ghatok at that time, and Professor R.K. Mishra. So we did some work on, at that time I wrote some codes in MATLAB, actually from taking cue from the book of Sullivan. So I'll mention that book later on also. And we used that code to basically analyze these coupled microstrip lines, and we sandwiched the slab with some of these media, which was double negative or dispersive media. So these kind of things, as I was mentioning, that these things can be modeled in FDTD. Today I just gave you the basic overview. So this can be done, and later on in my later parts of my talk, I will talk about, mostly I will focus about this two dipole kind of situation where I have. So maybe tomorrow I will start from here a little bit, like I will discuss about how to do all these things just a little bit before going into the my next part of my talk. And just to give you complete the discussion today, there are several of these commercial FDTD solvers. So XFDTD is there, numerical ANSYS there, 3D Maxwell solver for nanophotonic devices. So not only in the RF domain, you can, like in terms of opticals domain also, because anyway, like it is a general solution of Maxwell's equations. And we have this Keysight TM Pro also. And CST, well, it is a computer simulation studio. It generally has the transient solver. So it is finite integration technique, a relative of FDTD, you can say. So it has its own, this is just, the part that I covered today is just, you can, what you can say, just a small droplet in the ocean kind of thing. So, but anyway, I hope that I have tried to convey the message that we can write our own small update equation based codes using Maxwell's Carl equation, and we can demonstrate this wave propagation in the free space. And we can, some of these concepts I tried to discuss with examples, because if I only focus on the theory, I don't think it will make too much sense in this small span of time. And why we need this PML, this part I tried to highlight, and I tried to highlight on this how to choose the cell size and the time stepping and how the stability of the system is related. So this part I will maybe tomorrow I will also talk a little bit before going into the next. So I'll stop here and thank you for the attention. And I'll be happy to take any questions if there. Yeah, thanks.
Okay, thank you, Dr. Debdeep Sarkar. So it was a very nice talk from your side. And we have received some questions from the audience. So I'll go through those questions one by one.
Yeah, sure.
And you can answer.
Sure.
Yeah, before I request other volunteers, that is Rinki Ghoshal and Suman Pradhan, please share the feedback link with the participants over Google Meet and YouTube Live. Okay, so the first question is, how FDFD is different from FDTD in application point of view as well as mathematical point of view?
Yeah, so this I think this is a good question, because this I had a number of discussions on this topic. Like there is this method. I hope I am interpreting it correctly. Like wants to know about the FDM, like finite difference method. So yeah, I think one key thing is in the FDM, you can see from the name itself, like the way I understood that we have this time domain, time marching kind of thing over there. So that is one key thing. Another very important thing, let me go back to some of the formulations a little bit. I will just quickly go to that slide to show or to make my case stronger. So yeah, so let's say we have this thing. So in this case, it is completely explicit what they're trying to mean, that we do not have to go for any like matrix inversion kind of thing over here. So it is an explicit solver. But the way I understand the other solvers, when we, let's say we want to find out the charge distribution or the voltage distribution, do a exciting charge and solve all those kind of problems. So we have to go for some matrix inversion and implicit kind of formulation, a system of linear equation kind of thing comes into the picture. So these are the like some key differences I can say, and I will stop here. Yeah.
Okay, thank you. Next one is how reflection coefficient can be obtained using FFTD techniques.
Okay, yeah, very good question. I think so. How you can do that? Like, let's say I go into this animation over here. Yeah. So how we can do is like it is free space, so nothing is coming up, right? So, but if we place a medium, at some point you will get back some reflected pulse. So whatever, like let's say you or I will go to this one. Yeah. So suppose I have my source point here and I have my receive point somewhere located here. So just for the answering case. So if I launch the signal, it will come here and it will then come back, and some reflected pulse I will measure from here. So if I record the pulse values at this point and I have the information about the pulse values with the space of time, like as a function of time, so I will have two things. One is basically the source that I launched, and one will actually have the reflected pulse. So I have the knowledge of the source, so I can actually do the manipulation, and I can subtract that source part from it, and I can have that pulse like reflected pulse data only. So now you have two things separate. One is what you launched and what you got back. So when you have the information of these two time series, you can now get the Fourier transform of the reflected pulse, and you can get the Fourier transform of the like launched pulse over there, and you can calculate the reflection coefficient. So yeah, this is a very like important question, because this is what we do when we actually have this like I was thinking about talking about a little bit on this tomorrow. Like we have the two dipoles, so we launch something here, and we receive something here, and here we can use the procedure that I described, or we can follow the other route also. Like we can launch something here and get back the data here, and from the two-port model, again, like this is a second solution that I am talking about. So from the two-port model, we can calculate the two-port Z parameters, and from the Z parameters, we can get the S parameters. So there are various ways. So I hope I have answered that. Yeah.
Thank you. Next one is please comment on CFL condition in FD method.
Yeah. So like CFL, I think I like covered that part. Like I hope my screen is visible. Like I will go back to the slide while I mentioned. Yeah, so here I have clearly shown the CFL criteria, and the importance is, well, I think all the coding, whatever I have shown here, we call it conditionally stable FDTD method, because we are going for this forward difference kind of formulation, and we are using, like, there are various things. I will not go into the theoretical details, but the main thing is we have this constraint that we have the EM wave that cannot propagate in free space faster than the speed of light. So we need to have a basic like delta T based on the cell size. But there are ways to get around that, and people are working on this unconditionally stable FDTD method. So that is the research on the FDTD like algorithm level. But the criteria is basically represented here. Like when we choose the spatial cell size, we have a constraint on the delta T or the time step. And because if we go beyond this time step, it will result into numerical instability. So that is in a very nutshell why we have to follow this CFL criteria in formulating our FDTD equations. Yeah.
Okay. Next one is please highlight the difference among PML, master slave, and PEC PMC boundary.
Yeah, okay. So very good question, because it is needed in various like modeling. So I think in simple physical terms, today's lecture I already covered about the like electric field, like this PEC PMC thing here itself. Like when I talked about this, like that at this point, or let's say I come to this slide. So here we have the PEC boundary and we have the PMC boundary. So to enforce the PEC boundary, you need to like for a linear thing, you need to enforce that component of the field at 0. So in this case, dz equals to 0. Similarly, in this case, like in this wire dipole case, if you enforce the Ez equals to 0 at these points, we will get the PEC boundary condition. Similarly, for PMC, we have to enforce the magnetic field component. So here it is just a simple wire. But if we have a, let's say, a plane of things, so that plane actually we will have to make both the components enforce that thing as 0. So PEC and PMC, these are very basic. And PML, I already talked like how it is basically doing the numerical absorption kind of thing. And in terms of the master slave, well, I think it will be better from the FEM point of view, or like to that kind of nomenclature is there in ANSYS HFSS. So the idea is that we have to ensure that that is the periodic boundary condition. So there are like block modes, Floquet block modes, and kind of stuff like that to enforce this periodic boundary condition. So interested people can look into the corresponding literature. Yeah.
Okay, thank you. One small question from my side, that is,
Yeah.
in CSC Microwave Studio, we can find that there are four, in the boundary, there are 4 PMLs with 0.0001 reflection coefficient, means what I can see in my version. So whether individual PMLs are having reflection coefficient of 0.0001 and 4 such are being used together, so that the reflected wave is almost nil.
Okay. Yeah. So to be honest, I myself, like I have mostly used the HFSS. So I'm not aware of the entire, like what setting is there. But from physical point of view, what I can tell you is you can, like there must be, like when you, the objective is when you, encompass your entire problem space with PMLs, there could be provision to have a different reflection coefficient. Like I think 0.001 means very small, like reflection will be enforced from the slot coming out from the those layers. So I think individually at all the 6 faces, I don't know about 4, but in our case, like when we model this 3D thing, so this is let's say a rectangular or parallelepiped kind of thing, and we have 6 faces, or for a cube also you have the 6 faces. So there at the 6 faces we can choose like 6 layers of PMLs, and some of them will be overlapping based on the like which edges are actually touching upon. So individually those layers can have different, like you can model them to have different reflection coefficients. Also you can keep a certain, like let's say you know that in certain direction there is more radiation or more flow of your signal. So in that part you put more layers, in other part you put less number of layers. So I think those provisions are there. So that much I can say. Yeah.
Okay. Thank you so much.
Yeah.
The next one is how quiet zone analysis can be done using FFTD.
Quiet zone analysis, I am not sure. Like I think I have heard about these terms from the antenna measurement community. So I guess it's more like I have to maybe look it up. Like I am not sure. But if it is meant that like let's say you put these layers of absorbers and you want to get back the reflection, so those things again, like entire thing is based on how you model your system and how you collect your signal and you process it later on. So the process should be similar. Like if one wants to emulate the quiet zone measurement in an anechoic chamber, that is might be possible, but again for more like getting a large chamber simulated in a FDTD might not be the best advised method, and people have to look into some other techniques also there. Yeah.
Okay, thank you. The last question is, can you comment on effect of meshing cell on design analysis of antenna?
Yeah, definitely. I think, this is like if you mesh it, like I think in yesterday's talk, maybe I think like there was some discussion on it. Like in any case, like in any FDA, like in case of let's say FEM, you like when we model it in the HFSS. Actually, I'm talking about HFSS because most of my like antenna design work I did there. So generally, what happens is we take a solution frequency and we sweep like have a sweep around it. Like if we want to solve it for let's say 2.45 gigahertz, we sweep it from 1 to 4 gigahertz. So that is a kind of fast sweep, and that is actually extrapolated. So at the solution frequency, at the center frequency. So the meshing is done at the center frequency, but we get the S parameters for all the frequencies through extrapolation. But in case of instead of fast, if we go for a discrete kind of solution, you have the meshing done for all the frequencies. Your memory requirement will be very high and a lot of space will be lost. But again, you will do the proper meshing. So that will affect in the calculated S parameters. And that result that you get from the discrete simulation might be more close to whatever you get from the experiment. So yeah, meshing definitely is very much important. And how you mesh your antenna, sometimes you might need adaptive meshing also. Some regions might need more finer mesh, some region might need more coarse mesh. So all the types of things are there. So it definitely matters. Yeah.
Okay, thank you so much on behalf of IEEE MTTS Student Branch Chapter, Jadavpur
Thank
University.
you. Yeah.
So we are really very much fortunate that you have provided your valuable time and you have delivered this talk to the participants. So I think they got motivated, and they will be thinking on starting work on this particular domain. So tomorrow we'll be meeting with you in the second
Yeah.
half
Yeah.
at 2 o'clock. Okay,
Yeah.
thank
Sure.
you so much.
Sure. Thanks a lot, Ardhendu. Thanks. Yeah.
Thank
Okay.
you.
So I'm logging off. Yeah. Bye.
Yeah.
Bye.
Bye. Okay, so kind